Today we have Michael Young. Michael Young, how are you doing?
Hey Nathan.
Dude, we were before we started, I was talking about your background. So cool. I was about to change it to be as cool as you, but you got there first, so I didn't want to.
Hey, invitation's a serious, most sincere form of flattery, right? And in fact, this is not my background. Another person at Elastic was kind enough to share this out because it resonated with a bunch of us, right? If we're in tech, then we see what feels a bit of Iron Man-y, a little bit of semiconductor, right? And then of course the Elastic logo. So it's like, hey, I'm gonna steal it, I'm gonna use it. So feel free, right?
Geeky. It's like the melting of many geek in the world together.
Yeah, absolutely.
So Michael, you want to give some background? Just tell us about yourself.
Yeah, sure. So, for those of you who have not interacted with me, my name is Michael Young. I'm a senior principal solutions architect at Elastic, supporting Elastic's US PubSec, specifically the Fed DoD team. I've been at Elastic for a little over 5 years. I just hit my 5 year point a couple of months ago. It's been an incredible journey so far. But I've been using Elastic since 2011, give or take. So more than a decade, right? So long time Elastic user, open source, former paying customer, used Elastic in a lot of different ways. And, Elastic is one of those things that I'm passionate about because of the tech. And I've been in this space since 2003. So 21 years I've been doing information retrieval, big data, data manipulation and analytics, right? And all of that has been fundamentally focused on just being able to find the data that matters to answer your question, right? And so Elastic's really good at that.
Awesome. Our topic, and this is going to be a series, is going to be sizing. And many
Oh,
people consider Michael the maestro of on-prem sizing. So yeah, we're gonna do this in several parts, and I'm excited where this goes. Exactly. This is a topic we bring. First of all, why are we excited about this topic? What excites you about sizing? Why is this important to Elastic?
that's a good question. So it may seem a little weird to be excited about sizing. And I would argue that I'm not excited about sizing itself because it's just kind of in the weeds a bit, right? What I'm excited about is enabling people to think about the things that matter with sizing so they could be more informed. Because what I am excited about is training, teaching, mentoring, just helping people be stronger at what they're doing. And whether that's, my fellow elasticians or our customers or the community, that's really what it's about. So really, at the end of the day, sizing is something that I've been doing for multiple distributed products over the years, right? Elastic isn't the first distributed solution I've worked with. I'm a former Hadooper, right? So certified on two different Hadoop distribution type. Former job was at a Hadoop company, right? Sizing is an important part of managing these arguably complex distributed systems. And so because of all the variables that are involved, people don't know what they don't know, and things are great until they're not, right? And sizing is usually one of the things that's the first thing you want to validate, right? Not just in terms of getting started, but over time, as your use cases evolve, as your data volumes grow, as your user base grows, you want to make sure that you're maintaining, the health of your cluster. Sizing is core to that, right? Just like if you have your vehicle, you're supposed to be checking the oil and the fluids, right, on a regular basis. If you don't, what happens? Well, your car might go 100,000 miles or you might get 50, right? And now all of a sudden it's in the shop. So that's the idea is if we can educate people on sizing, then the hope is that, teach them to fish, right?
Yeah, I think one of the things I love about sizing is Elastic is fast, like crazy fast. A lot of that has to do with sizing. And I think some people, when they hear that, they think, oh, it's fast, yada, yada, yada. And then they install Elastic and they're not really cognizant of what they're putting in and not trying to go after the speed. And they get that ho-hum speed and they consider that acceptable. But with a few tweaks, and that's why I think this is a very important topic, a few tweaks here, understanding a few things here and a few things there changes that cluster from a ho hum, we got this to work, to this is so fast, this is fun. Like fun comes in at speed. And I feel like that is a big element of the sizing right there.
Yeah, no, I think that's a very, very astute observation, right? It's one of those sort of things where people don't realize how fast Elastic can be, right? I think right now we target somewhere around, like a 250 millisecond average response time for a typical query, right? And that's fast, right? That's a quarter of a second, and I would argue that if your query was taking a half a second, you probably wouldn't notice the difference between a quarter of a second and a half a second. But when you think about more complex use cases that are actually real time. So think about fraud interdiction, right? Think about every time you swipe your credit card. I've had this happen to me more times than I care to admit when I go to Home Depot, and I hit Home Depot 3 times, 4 times in a day. Why? Because I don't make a list ahead of time, and I inevitably forget something. And then eventually my credit card's like, "Hey, this charge is declined." And I'm like, "What? I was here like an hour ago, right?" And it's because they think that's suspicious activity. That sort of thing happens very quickly, right? And so Elastic can actually get down, right? If you architect it properly, and to the topic of sizing, right? If you size your cluster well and you give it the right hardware, you can have single-digit millisecond response times, right? Like that's mind-boggling to think about. But guess what? Not everybody needs that, right? And so out of the box, Elastic has same defaults that will work for the broadest spectrum of use cases. And to your point, like it will work well, right? But not everyone needs the push, right? They might want it, but they don't need it, or they don't have the budget for it, right? And I think that that's the thing that excites me about Elastic is we like to call them nerd knobs. Elastic has plenty of nerd knobs to adjust the sizing and the performance of the cluster so that you can balance your price, performance, budget, and requirements, right?
Yeah, that's a great point. I mean, this is the Nathan's elastic cap coming on, but like to that last point, I mean, if slowness is acceptable, there's a lot of use cases that slowness is very acceptable, and our license. I mean, there are a lot of people who have bought our license literally because allowing them to go that slow was acceptable, and it was cheaper to buy the license than the hardware needed to have a solution otherwise. So
yeah, absolutely. And I would say a prime example of that, and I'm sure we'll dive into this at some point, right, is the concept of data tiers, right? Being able to manage that. And we have a blog, where we demonstrate the ability to query a petabyte of data on a single Elastic node. And we run have a bunch of benchmarks on that, right? And the initial query takes something in the neighborhood of like 10 minutes. And for most of us at Elastic, we're thinking 10 minutes, man, that's an eternity. Like, who would be happy with that? But then, a lot of people are like, well, 10 minutes is a heck of a lot faster than never, right? And that's the reality is for a lot of organizations, the ability to query a petabyte of data at all is incredibly difficult, let alone to be able to do that on a single node, right, of any tool. So, and again, it's about what are your requirements. And so I think that we can be a race car, or we can be a family hauler, right? It's whatever you need to meet your mission requirements. And the reality is you don't know what you don't know. So let us figure out how we can help teach you the things that matter, and then give you that knowledge so that maybe you start with something that performs very well 6 months, a year, 18 months out. You're like, you know what? This isn't performing as well as it was a year ago. Why is that? Well, it's, you probably have put more data on than it was sized for, or maybe you've got some configuration settings you can tweak. And so I think there's a lot of things that we can really share with the community to help them.
Awesome. All right, let's, before we start, and what we're going to do is we were thinking of going high level first and then diving deep generally is what we're thinking of doing. Walk through what people should expect in this series, beginning to end. Should they, like, to help them understand, is it worth their time to actually listen to the series or not?
Yeah, I think that's important, right? I think today, a lot of us, I won't say most of us, but I'm pretty confident in the idea that many of us consume videos, right? YouTube. I know, for instance, short story, right? Love stories. I've got a Cup Cadet riding mower, not a brand endorsement, but I love it. And it's not very old, but yet the throttle cable went out. And I'm like, well, I know that can be replaced. I know I can go order the parts online, but I've got no idea how to do that. What's the first thing that I did? I went to YouTube and I looked for a video that showed me how to do that. And most importantly, I didn't look for a video that was an hour long. Like I wanted this should be a 10 or 15-minute job, right? Based on my experience, doing some of these mechanical things. I'm like, I just need to know, like, what's the piece of information I'm missing? So the hope is that we're going to create these bite-sized nuggets of information that will be, relatively focused in a topic area that allows you to, target the information you're most interested in. And if you find that there's another element in the series that you're interested in, you can dive into that, but you don't have to sit right for an hour and then remember to come back and continue that. So that's the hope. And so it in terms of like the format, right? And in terms of what we're hoping to cover, the idea is start with the higher level concepts, right, of Elastic and the nature of sort of distributed systems, right? And then how Elastic goes about managing data, right, in a distributed way, and what aspects of Elastic and hardware, right, and the data matter for you as a user of Elastic to be able to configure all that. So we're going to start pretty high level, just let's set a foundation, and then the hope is we're going to build, our house of knowledge on top of that foundation, right? And so as we go along, the idea is that we're going to get a little bit more detailed, but it's not always going to be like progressively more detailed. Sometimes seeing is believing. So just doing a screen share and showing you how to do something like, an ILM policy. Yeah, the idea is that people are going to be able to consume these at their leisure and hopefully in a time commitment that is just more manageable for today's, go mentality.
Awesome. Okay. Thank you for that. Let's dive in. Tell me, I think a good place to start is data tiering. Why does it exist? What is it generally? What is an elastic cluster? And yeah, walk through that.
Yeah, no, I absolutely happy to do that. So you know what? Let me go ahead and share my screen because I think there's some value in just having some visuals. And to be clear, right, I am not going to slideware you to death, right? The idea is I'm not going to draw this out. I don't really have fantastic handwriting or drawing ability. So I've got some, things that I'll drag over here to make it a little more visual, right? Because I'm a visual learner. If I see things, if I see colors and shapes, it just helps me retain that information. So like what is Elastic, right? So Elastic is the company that are the founders and curators and maintainers of the Elastic Search AI platform, right? If you've been in the space for a while, if you've been in information retrieval or the search domain like I have, you've probably heard it as Elasticsearch, ELK, the ELK, right? So there are multiple names for all of this. And fundamentally what they're really talking about is, the platform, which is a search platform at its core, right? And that's really what makes Elastic different than other solutions, right? So if you think about a database, for instance, it was designed to solve a particular use case. Things like, transaction processing and analytic processing. The way that you interact with that, the way that you performance tune that is, for specific kinds of use cases, and it does that really well. And, what customers know, what the community knows is at the end of the day, everything that we do is about the data. I have to be able to get to the data to be able to answer my question, to be able to get through the analytic that I'm doing. And, not all tools are well suited for that, finding the data aspect, right? And so that's really what makes Elastic stand out is the fact that first and foremost, we are a search engine, right? Whether that's a historical lexical search, like say keyword search, like Google, right? And it's also vector search, right? I'm sure you've heard it's kind of all the rage these days, right? Over the last 12 months, maybe generative AI, right? Retrieval augmented generation. Those are all things I think that they're exciting in terms of what their potential is. And what people may not realize is that to do any of that stuff, you've got to be able to find the data that matters and feed it through those processes, right? So at a high level, that's what Elastic is, right? We are a search AI platform that's all about getting you access to the data that matters. So any questions or follow on just sort of that explanation? Because I want to start bringing some visual elements in here, I think.
Yeah, I was kind of expecting you to hit the visual stuff. No, that makes sense. Keep going.
All right, fantastic. So you should be able to see my sort of whiteboard here, right? Yeah, fantastic, right? So when we talk about like Elastic, right? As I said, it's a search engine. Fundamentally, at its core, that's what it is. And so when you think about the ability to scale, many of us have constraints, not just in the workplace, but at home. Whether it's our salary, right, and our budget, and how much home we can afford, there are limits to all things, right? And data is no different, right? And so when you look at it from a mission perspective, as much as the mission dictates that we should get all the things that we need to do our job, that's not always true. The money isn't always there. The hardware's not always there, right? So, when you're looking at solving security problems, observability problems, right, and search problems, really anything with data, you have to be aware, right, that there are going to be finite limitations placed on you as an organization, right? Typically budget is key, right? But sometimes, and I live this, right, as a former customer, finite amount of space in the data center. Like we had budget for servers, but no place to actually put those servers. There was no power, space, and cooling, So figuring out, okay, well, in the physical space that I have, what can I do, right? And so just kind of laying that as the ground floor is that we know there are limits. And so Elastic is inherently designed to be flexible so that you can design it, put it in place, and then I would say most importantly, evolve your deployment over time, right? And that's the thing, you're never painted into a corner, right? So from a resource perspective, like what are the things that really matter, right? So let me go ahead and drag these over here. So this is not a purely elastic concept, right? If you're talking about data, a data platform, whether you're talking about things like data lakes, right, data warehouses, they have very similar constraints. And that is there's only so much compute resources that are available, right, within a given architecture. So these are all concepts that you should be familiar with, right? CPU, RAM, disk, and network. And so while we do provide some minimum recommendations for how many cores you should have on an Elastic server, how much RAM, how much disk, and what your networking configuration should look like, those are rarely firm number. CPU is heavily used quite a bit in Elastic for the intense processing, right? When you're doing things like machine learning, right? That's a very CPU heavy workload. RAM is, where all the fast access for things are from a caching perspective, right? You've got to be able to hold certain things in RAM so that it's very performant. Disk is, that's your value store for your data, right? That's where things are going to sit in bulk, right, in much higher volumes. But the trade-off there is disk, right? Even if you're talking about NVMe storage or SSD, it's multiple orders of magnitude slower compared to RAM access, right? And then of course network, right? Obviously, you got to be able to connect to where the data is to bring it into your cluster, right? And so there's a finite amount of network bandwidth that's available, not just on your servers, right? Because you might have a 1 gig or a 10 gig network connection on the server, but then there's also just the network backbone itself, right? What does my switch and router, and firewalls look like? So there are natural limits here that are going to exist on an Elastic node, right? And in traditional data storage systems that aren't inherently distributed, the problem they run into is they hit these limits, and fundamentally what that means is they can't add more data to their infrastructure easily, right? You've hit the limit. You're consuming all of the CPU, you're using all of your RAM, you have no more disk space available, you're saturating your network. What are the next steps? Well, the way that is solved in modern architectures is distributed systems, right? You spread the data across multiple servers, Docker containers, virtual machines, right? Physical servers. When I say server, I'm using those concepts interchangeably. And the value there is that you get access to the same resources, right? Multiplied, right? Many times over. Okay. And so that's the fundamental value of a distributed architecture, right? At its highest level is that you get the ability to take advantage of the resources of all of these systems, right? Seems simple at a high level, but the hard part is how do you manage all that? How do you know where to put data within these systems, right? Oh yeah, absolutely. Yeah, feel free to interrupt.
I'm going to throw you a curveball. I think I might answer it myself because you don't know where I'm going with this one. But we've all shared this to the peanut galleries before. And common thing I hear is a CPU RAM disk. When I say we need this much CPU, the hardware junkies in the room will say, what type of CPU? What type of RAM, what type of disk, what type of network, because not all of them are created equal. 100% correct, right? Like, I think we would all agree that there are different ways you could do RAM. And sometimes when a software company says, I need 8 gigs of RAM, some RAMs you could get away with 4 gig. That's very possible, right? Those games can be played with specific type of hardware devices that exist. So we acknowledge that when we look at AWS's history, the Amazon cloud, they kept it this simplistic at the beginning. But if you look at their services they provide now, it's not as simplistic now. But I think this is a good place to start. Start the discussion and get your hardware person in to tell them, hey, we're a Java app, we use Java Heap, all those things. And they might have different opinions, but this is the place. Assuming everything we're going down, this is the place to start. And tell me if you think differently on that.
Yeah, no, I think you're right. I think there are a number of variables. In fact, I was at a customer. I was out in Colorado a couple of months ago, right? And it was a great discussion. We were doing a bunch of whiteboarding, and we were trying to help the customer understand, And there was an infrastructure person in the room, right, who isn't going to use Elastic. Their job is just to manage the virtual machines and the storage and, and the NetApps and the EMCs. And they're like, tell me what you need, right? I'm like, well, that's what we're working through, is to figure out what you need from a sizing perspective. And they don't know what they don't know. To them, do I provision out a bunch of spinning disks, like we call, Rust, right? Because it's mechanical, and those are great. They have great data density, but they're slow, right? But again, slow may be, slow is very much a subjective thing. And so what I think is slow may be perfectly acceptable for a customer. And then they're trying to figure out, well, do I have SSD storage? Do I have NVMe flash storage? How much of that is available? And so I think one of the pitfalls that people fall into is they make the assumption that all these things are the same, or what I know about my last install, I need to copy that because that's the only way to do it, right? And that's the pitfall, is that no, there are dozens of ways that you can set up a cluster, not just from an Elastic perspective, but other distributed solutions, right? You can change the CPU, how much RAM you have available, and the type of disk to give you different performance profiles, right? And no one profile is perfect for everybody. There's certainly a catch-all that'll work for many people. So I think that, from an Elastic perspective, the most important takeaway is that while we provide recommendations, and there are certainly, stratifications of the types of these compute resources that will impact performance, there's very little in the way of thou shalt do this thing, right? To your point on RAM, does the speed of the RAM matter? Not really, right? Because when you're talking about distributed processing, the speed of the network is nowhere near as fast as what RAM can do. So you adjust your RAM speeds, right? You're probably never going to notice a difference. Now, if you're on a single node and it's a high performance computing environment, well, that can make a difference, right? But in a distributed architecture where the network is a key part of how these things are sharing information and communicating, like worrying about, the type of RAM is just not worth the effort, right? It's more important to think about how much RAM do I have, right? Likewise, same thing for disk, right? You can think about disk as I need 20 terabytes. Well, 20 terabytes of what? SSD, spinning disk, is it 15,000 RPM? Those things will impact the performance of the clusters. Happy to dive in and clarify around that. But I think there's so many different not rabbit holes, but different angles you can go at. We don't want to do that without being thoughtful of the time.
I'm with you. I don't want to, I probably overcomplicated it, but just, it's a good place to know we're simplifying this, worthy of discussions, but this is a great place to start. So I'll let you continue.
Absolutely. Yeah. So, so the idea is that in, modern distributed systems, as we add data to a cluster or to a node, at some point, you're going to hit the limits of what that node can handle. And that's either more of a soft limit in terms of performance, right? So you have requirements that data be a certain performance. Your queries come back in a certain amount of time. There are organizations that say, this project has a mandate, a service level objective, an SLO, that I've got to respond to requests in a certain amount of time, right? You might hit that limit where, it's not a hard limit of the resources, but you're hitting that time limit, right? And you're not meeting your or you actually hit physical limits. There's only, data has gravity, right? There are physics involved with data, right? You're writing bits to a medium that you can read back. And there is a finite amount of that on any given system. Like even the cloud is finite, right? Sure, it seems like it's not, because behind the scenes, they can add resources and make that all available and make it transparent to us, the consumer. But, there's only so many active data centers, right? So over time, they're constantly looking and evaluating their back end. So you're going to hit either a hard limit, you've used all of the disk space on the server, or you're loading more data into RAM than RAM you have available. You had mentioned a little bit earlier about Java and heap, right? Elastic, at our core, we're a Java application, which means that we use Java and the JVM heap, right? The Java virtual machine heap. There are considerations around how much RAM you have and how much you allocate to heap, right, that have an impact on your cluster. Now, to be clear, there are a lot of things that we do that are off heap. The realities of that is because you need to do that for performance reasons, you need to do it for scaling reasons, but the heap is certainly something that we can talk about, right? And that matters. I think that big picture, if you were to go look at a recommended Elastic architecture, we'll often tell our customers, what is a typical Elastic node, right? It's 8 to 16 cores or vCPUs, right? That doesn't mean you have to have that, right? We have customers that are spinning up much smaller instances of Elastic in Docker containers. You can run Elastic on a Raspberry Pi. right? You don't have 16 vCPUs. You don't have, 64 gigs of RAM, right? So you can absolutely run Elastic in much more resource constrained environments. But the caveat there is you're trading off performance, right? And that's okay. If you're happy with it being slower, then great. Your mission, is successful. The other aspect is the data volumes, right? As I said, data has gravity. There's a finite amount of data you can put on any given server. Raspberry Pi is no different as an example. A Docker container in a laptop, is going to be more limited than something I spin up in the cloud. So while we will provide recommendations to customers, I think the biggest sort of rut that people will fall into is assuming that it always has to be this way. And the minimum is I need all of these resources. And that's simply not true. You can actually get started in a really small configuration. Does that make sense?
Yeah, makes perfect sense. Absolutely. We are very versatile, Java app, but we have a max based on, which we'll probably dive into deeper as we like what a maximum amount of CPU should be on a Elastic node. But yeah, almost anything below that is doable.
Yeah, absolutely. So one of the things that a lot stands out from an Elastic perspective is if you've got any experience in more traditional non-distributed systems, when you hit that limit of a single server, typically the first thought is, well, I need to add more resources, right? Why? Because it's not a distributed system by design, and you can't just add more servers. So what do? You make the servers you have bigger, right? So that means giving them more CPU, more RAM, more disk. And where I think historically you would see this is with databases, right? RDBMS, relational database management systems were not known for scaling out. They were known for scaling up, right? But again, you're going to hit that limit of what a single server could do. Eventually, right, no matter, you just can't continue to add resources, right? There's a maximum amount of RAM that you can put on a server. Now, that is evolving over time. The number of cores and the number of actual CPUs you can put on a motherboard, have naturally increased, right? The amount of maximum RAM on a server has increased. But, at any given point in time, there's a limit, right? There's slots. You can only put so much sticks of RAM into those slots. So, and that's where distributed systems come in, is the realization that if you're able to spread your data and your workload, so we're talking about workload, that's the queries, that's the analytics, that's the machine learning, right? The indexing of the data, right? Or the storing of all that data. If you can spread that out over multiple servers, then for all practical purposes, you're not limited in what you can do. And so that is really the core of what is Elastic is, being fundamentally a search engine, right, is fantastic, but it's a search engine that is distributed by design. So a single node of Elastic is a cluster of one. And so you as a customer spin up a single node of Elastic, and then you say, okay, this is great. I'm getting some real value out of this. I'm able to, be mission effective, but I know that I need to add more data. And so you can continue to add data to that node until you hit those finite limits, right? Well, the really cool thing about Elastic is that you can add multiple nodes to your cluster. And when you do that, Elastic is going to spread that data around for you. You don't even have to think about it. Like if you do nothing special out of the box and you stand up multiple Elastic nodes and they're configured to talk to one another, Elastic is going to handle moving all that data around. In a non-distributed way, you, right, the data scientist, the data manager, the ETL person, the sysadmin, you've got to think about, well, where do I put the data? How do I manage the queries that are going across all of this? As a customer of Elastic, this is all done quite arguably automagically, right? From the end user perspective, you just don't need to know about it. How does that happen, right? So as I said, you can start with a single node of Elastic. And again, it can be a single Docker container. Great, right? But as we scale out, you're going to want to add multiple servers. And the one rule of Elastic that fundamentally you can't get around is that you can go from one node to three or more, right? A 2-node cluster is not a viable cluster, right? That doesn't mean you can't use it, but you're inherently limited in what you can do, because Elastic, most distributed systems uses a concept of a quorum, right? Which is you got to have an odd number of entities that are voting on, well, who is in charge right now and knows what's going on. So the one hard and fast rule with Elastic is you got to have at least 3 nodes to really have a properly distributed system. Now, you could have 5, 7, 10. They don't have to be odd numbers of nodes. It just needs to be at least 3 once you start getting into the distributed model.
Yeah, I think that's a good topic to jump into. Talk about the split brain conundrum. why, and this is not just an Elastic thing, this is, to your point, an industry-wide thing. So yeah.
Yeah, so split brain is it's a concept or a situation where in a network environment, right, for redundancy, high availability, and fault tolerance, right, what you typically are going to be doing, and this isn't just from a distributed application perspective, but from a well-designed architecture perspective. Think about data centers. If you've never been in a data center, right, they're not filled with desktops, right, that most of us have, or laptops, right? What they're filled with are racks, right? They're typically 42U, right? Those are 42 units. A unit is one small sort of server. Again, I'm simplifying here because there are things like hyperconverged architecture and blade chassis and things like that, but data centers are filled with racks of servers. And so even in non-distributed kind of concepts from an application perspective, you think about it just from a data center perspective, you're going to have all of these resources. So you've got racks with multiple servers, you've got storage, you've got top of rack switches, right? And then there are switches and routers above that. And those are all done to give you fault tolerance and high availability. So if you were walking to an AWS or a GCP or an Azure data center, it may look a little bit differently, but conceptually, it's a bunch of racks with a whole bunch of high availability, right? And so the value of that is that if you lose a rack, the idea is that you haven't lost capability, right? Sure, you've maybe lost some capacity, but your data's still there, your processing is still happening, your analytics are still happening, right?
Everybody knows every computers go down.
Exactly, right. And in fact, right, one of the ways that this is talked about and often I think, joked about is the concept of, pet versus cattle, right? With pets, when they get sick, you take them to the vet, right? You want to get them the medicine they need. If they need special food, right, you got to make sure you take them out for walks and get exercise and things like that, right? Of course, pets being, cats and dogs and things like that in this concept, right? But the idea of like cattle, right? Like they're going to get sick, right? The cattle generally are raised for a purpose. It's meat, right? It's dairy, and so you don't want, anyone in your herd to die, right? Or meet an untimely or early demise. You don't want that, but you accept that that's a reality, right? You will certainly, make investments in having the vet come out and do kind of preventative maintenance, things like that. Yeah, absolutely, right? But the understanding is, in the IT world, in the infrastructure world, right, the same concept exists in the cloud. Like you have to accept that you're going to have a minimum level of failure on any given day, in any given hour. There's going to be things that are failing, right? Whether that's disks or storage or servers or switches, right? They're going to fail, and so you need an infrastructure that will allow that to happen transparently to the applications, transparently to the services, and transparently to the end consumer, right? And so the idea is I think in a more monolithic architecture that is not distributed, it's much more like a pet. Like that server can't go down, right? But in a distributed architecture, you accept it. Well, no, it's more like cattle. I may lose a server. It's going to happen, but the system's going to be able to just continue functioning when that does, and that's going to give me the time to respond to that, right? To replace that that failed piece of hardware, the failed server, whatever.
So bringing that to, say, like the split brain, knowing that something will go down, everything else needs to know who the leader is, because the leader gets to decide what happens when new data comes in, where is it going to go, how long is it going to stay. So one of those servers needs to be the leader of that. But if there's two of them, then they both have as much power to say they're the leader. That's
right. And so knowing that servers can go down, right, what's going to happen is say that I have a leader in my distributed, system, and that server goes down. Well, guess what? The other servers need to figure out who's the leader, right? And the hardware goes down, that's one thing, but you also have something known as like network segmentation, where a portion of the network goes offline. And in the cloud world, right, you would see this with availability zones, right? You may lose access to an availability zone, whether it's a data center to data center communication problem, or maybe from your infrastructure, maybe you have a dedicated link, but for whatever reason you're having a lot of packet loss, right? And so you get the one AZ fine, but the other one you're having issues, right? Again, just kind of throwing out sort of worst case scenarios. In a distributed system, somebody's got to decide who is in charge in terms of just managing state. What do I have? Where is it? What's up? What's down? The state of the application needs to be known and managed. And so somebody's got to decide that. And so to your point around the question around split brain is, we know that inevitably we're going to lose resources, right? And whether that's a piece of hardware like a server or a piece of hardware like a switch, you run into a situation where effectively half of your distributed system thinks the other half is gone, right? Whether that's because it, failed to check in on a heartbeat, but they both think that they're in charge. And so what ends up happening in a split brain scenario, right, is effectively you end up with two clusters that are working autonomously from one another, and they're changing state differently. And then when they get back together, now you have a bunch of conflicts, right? In terms of figuring out what is the accurate state of logs information, for instance, or my, distributed traces. And so when you have an odd number of systems that are voting, right, to get this quorum, it's really hard, right, for you to lose just one system and that break things, right? And so that's the value of having an odd number of voting, master eligible or coordinator eligible, right, roles. But people often say, well, if 3 is great, right, 5 is better, right, 7 is better, and it's like, well, you do get more availability, right? But in the Elastic ecosystem, there's only ever elected master at any given time. Everyone else is a master eligible node. They're aware of the state and they have the ability to vote on a replacement master if the primary master, if the elected master goes down, right? But only one master at any given time is the guy in charge, right? The person in charge. So having 7 masters doesn't improve the performance of the master. It just gives you more copies, right? And at some point there, you just reach diminishing returns. So hopefully that answers the question around split.
Yeah, this is good. And I took us on a couple tangents, and we're nearing the end of the time for this. So let's make sure we close up this topic, and I'll talk a little bit as you think about what you want to make sure you talk through. What I think we've talked about so far is what is an Elastic node, what is Elastic, like what search is, how it uses a node, and the value of distribution to search and to those nodes. And holistically, we talked a little bit about that split brain. What is the value of going from 1 to 3 and skipping 2? I think this is a good place to close up the concept of distribution of nodes. What are we missing, Michael? What are some things that we have not talked about that need to be brought up on this topic?
Well, I mean, there's a lot to this, right? So we can peel back the layers of this onion, right? If you will, there are, how does Elastic do this, right? One, fundamentally, how does Elastic, the fact that we can create an Elastic cluster that has multiple nodes and Elastic is going to intelligently move the data around for me. Great. Awesome. I don't have to do anything, right? Well, no, the point of sizing is to understand how you manage the data so that it is most cost effective, right? So this gets into the concept of data tiering, which you had asked about before, right? So that is a fundamental.
Yeah, that might be good. It might be good to tease data tiering today.
Yeah. So we'll leave a teaser. I think that's probably a good thing to we'll dive into in the next series. But I think that's also going to be tightly coupled with the way that Elastic stores data, right? So, from a data tiering perspective, Elastic has 4 data tiers: hot, warm, cold, and frozen. These are probably terms that you're familiar with. They're probably terms the community is familiar with. It's a very interchangeable thing, not just from a software perspective or a cloud perspective, but hardware vendors like storage vendors have the concept of automated data tiering as well. What is that? The idea is that not all data has the same value, right? Inherently, particularly for things like logging and security events or application traces or even metrics, right? When you're talking about event timestamp, time series based information, older data, not always, but typically is less valuable than newer data. So do you want to go buy that really incredibly expensive flash storage device and put all your data on there? Well, I think as technologists, all of us would love to do that, but we can't afford it, right? So you start making choices, right, about, well, if my design only supports that flash storage, do I make the hard decision of dropping data when it gets to a certain age so that when I do need to look at it, maybe I have to rehydrate it, right? Or do I think about things in terms of data tiers where I can have the system, right, or a solution in place that's going to put the data as it ages into a tier that is relevant, right, for that performance, right? It's the performance, price trade-off. Hot tier is the most recent data that's come in the last minute, hour, maybe couple of days, right? Single digit days. Warm tier, right, inherently is slower, right? If we're just sort of simplifying things. But you know what? What a lot of people think about is, Well, warm tier is slower, but in an elastic configuration, you may be surprised to see that if you run a query on the hot tier and a query on the warm tier can be as fast as the hot tier, right? People don't think about that. They go, oh, well, the warm tier is going to be slower because it's warm. Well, no, the big difference between hot and warm is hot also does all of that ingest, right? The indexing of the data and the ingest pipeline. So it has to have some spare capacity to do that in addition to the queries. The warm tier, its job is just to do queries. So it holds nominally twice as much data as the hot tier. Cold tier, likewise, is the same thing as a warm tier. It's not doing a heavy processing of data. Its job is to respond to queries, but it's going to do that by being a little bit slower because you're putting more data in the cold tier, right? From a hardware perspective, the hot and warm tier probably look identical in most scenarios, right? The cold tier is where we start to often see customers consider things like spinning disk. The performance trade-off of going from NVMe flash, SSD to spinning disk is well worth it. So think about things like in the DoD space, right? CCRIs, right? For the Army, where you have an inspection, you need to be able to show that you can pull back from an RMF perspective, right? Risk management framework perspective, the ability to query things from a year ago, right? 365 days, cold tier is perfect for that. But if you're trying to run queries in real time at sub-second response times, you might get that in cold tier, but that's really not what it's designed for. And then the last thing is frozen tier, just to kind of wrap this up. And this is a teaser for what really sets Elastic apart. Many products and solutions out there talk about a frozen tier. That frozen tier is effectively an archive that you have to rehydrate in some way to get value out of. That is not the case with Elastic's frozen tier. Our frozen tier is fully interactive, right? So your dashboards, your queries, you can interact with that data without rehydration. And what's really cool about it is that we use a caching layer where the bulk of the data is stored on an object store, like an S3 compatible, Google Cloud Storage, Azure Blob Store. You have the flexibility of storing that out on a cost-effective object store. And the data sitting on the object store, Elastic doesn't care about from a costing perspective. So when you're thinking about how do I manage my large volumes of data, right, you want to start thinking about not just do I have the right number of nodes, am I considering the right tiers for what my mission, use case, and requirements are? And so I think that'll be a good teaser into our next session.
Awesome. Michael, thanks so much, man.
My pleasure.
Next week.
Yeah, looking forward to it.